To the seminar. Hello again, welcome to the seminar. In this session, Guillaume Mahey is visiting us. He's a visiting PhD student, working with Joaquin and myself, and he works on optimal transport. Currently, he's working on unbalanced OT. He's supervised by Gilles Gasso and Laetitia Chapelle. He will be here with us between, he started two weeks ago, and he will be here until January. So part of his work has just been accepted at URIPS, and he will hint a few bits of the work he's currently doing now. So thanks, Guillaume, for visiting us, and we're looking forward to your talk.
Thank you for the introduction. So yes, my name is Guillaume Mahey, and I will present you a talk about the Wasserstein distance on the proxy of the Wasserstein distance as an application and statistical. So this is joint work with my supervisor, Gilles Gasso and Laetitia Chapelle, and the collaboration also with another PhD student, Guillaume Mahey, his advisor on collaboration. And I also would like to thank Felipe who helps me with the slides. So, okay, let's start. So the objective of the talk, there is three objectives actually. So to introduce to you the Wasserstein distance and what we used to do with the Wasserstein distance in the machine learning community, or more largely with in data science. In the second time, we will introduce Sinkhorn, which is a kind of modification of the Wasserstein distance, which is a kind of necessary. We will see why. And in the third time, one of my contributions, which is called SWGG, I will tell you more about this in a few minutes. Okay. So let's start with the paradigm. So generally in machine learning, we suppose that concepts are encoded as continuous distribution. So you can see as concepts like, for example, images, text, and stuff like that. So, for example, the concept of face, of the human face, is a distribution over the space of image. But in practice, we only have access to a discrete realization. So, we don't have like all the faces, all the human faces, only a few of them. And so, for example, this face was generated by general again like machine learning. Okay. So starting with the Wasserstein distance. Okay. So the Wasserstein distance is a distance between probability measures, that's the first thing to say. And it compares the distribution by moving one to another in an optimal way. So basically what we do is when you have two densities, you can move the blue one towards the orange one in an optimal way. So optimal stands for in this talk square Euclidean cost, but it can be what cost you want. It doesn't matter. It matters a bit, but in general you can talk many costs. Take many cost. And the nice thing about the Wasserstein distance is that you can think of the way of moving the density one to another in a horizontally way. So it's quite informal, but I think it's a good thing to have in mind. Okay. Okay, so in this talk, we only deal with a distribution which has n atoms and uniform masses, the atoms. And so what we are seeking for is a transport plan, so a way of moving the distribution from one to another. And so basically we are going to move one atom to another, and we will have a transport plan. So this transport plan is all the information of how we are moving a distribution from another. So starting with this example, for example, let's in the orange distribution be x1. So we are moving x1 to y2, So it is encoded on the transport plan, which is a matrix, as these green points light up. So the transport plan has encoded as matrices, like I said. And the first thing to say is that the transport plans which are optimal are necessarily sparse, meaning that it's unoptimal to have like a split of mass. So let's put a bit of formalism on this. Maybe I should use yes, okay. So basically, we are minimizing over a set of transport plans, so a set of matrix. And this subset U encodes like the conservation of mass, so meaning that we can only move a particle to another. No, so every particle must be mapped, basically the idea, and then you sum all the distance. So basically, you sum this distance plus this distance, etc. So let's check. Sorry. So just to be a bit more formal, so when we are dealing with this subset of positive matrices, which sum the column to 1 and the row of the matrix to 1, also to the vector 1. The first thing we can say is that this subset is convex, actually, on the subset of positive matrices. And the vertex of this subset has the permutation matrix. So yes, that's it. And it's solving the Wasserstein distance it's a linear program, so it's a linear objective function on a convex subset, so it's a linear program. And we because it is a linear program, we know that the optimal solution will be necessary on vertex, so necessary on the permutation matrix. Just to mention that in one dimension, it's a bit more different because solving the Wasserstein distance is way more simple, just because we can sort the two distributions. So and map is like the first with the orange, with the first of the blue, the second of the orange, with the second of the blue, etc. So we do not have anymore like this cubic complexity of the number of atoms, but this time it's just n log n complexity, so much more faster algorithm. Okay, so we are going to speak about some application of the Wasserstein distance. So the first application we can think of is like to compare, like you want to know like if two distributions are equal. So basically you have a distribution which is known and one which is unknown, and you want to test if they are equal. The nice thing about the Wasserstein distance, this compared to like usual loss between distributions, like for example the KL divergence, it captures this state, meaning that you have an intrinsic idea of the geometry of the distribution. So that's why this kind of thing works pretty well. Another example is loss in a machine learning pipeline. So come back with this idea of concept of images as distribution. So you want to map distribution to another and do a sampling on this continuous distribution. And it works because of a property of the Wasserstein distance that it metrizes the weak convergence measure. So basically, if you have two measures going to the same one, like converging to the same measure, so the Wasserstein will converge to 0. It's equivalent. So that's the nice thing. So basically, you can minimize the Wasserstein distance to make the two measures.
Excuse me, I don't understand very well. In the previous one, and in this example, you are speaking of some hypothesis test, some statistical problem.
Yeah. So this one is like is a statistical analysis, like
okay,
like
so you are speaking. This is an hypothesis. Some that is you are a zero, and there is some alternative, or not, or I'm lost in this sense.
Sorry, I missed the short answer.
I do not understand. This is a sort of H0 hypothesis?
Yes, yeah,
This is the H0.
yeah,
And you solve it with the
Wasserstein distance.
okay.
Yes.
And in the example, what do you in the example you is an example of this problem or
No, it's another
question?
it's another application.
Okay, thank you.
Sorry. Okay, so we'll move to the third example, which is domain adaptation. So in this problem, we have two data sets. So one which is already labeled. Let's say that it is the blue one, for example, and one which is unlabeled, the orange one, and you want to transfer the label from the blue to the orange. So you want to infer like the label of the blue distribution towards the orange distribution. So in order to do that, you can use your optimal transport plan, so compute the transport plan, and then the transport plan will infer for you like the label. So basically, it will map this cluster on this cluster, on this cluster, this cluster, on this cluster, and so you will know that because this corresponds of bags, this one doesn't correspond of bags. So this application uses the optimal transport plan given by the assumptions. And the last application is in trajectory inference. So basically, you have a population which move in time, in discrete time.
In the previous one, but you can. It is not of the permutation matrix. No, here it is different because you can have different number of individuals in each set. No?
So yes,
so here is a real transfer of mass. They are not only the transfer of individuals.
So yeah, also this application you make the assumption like in each cluster there's the same number of
you make like individuals. Okay.
Yes. So in trajectory inference, so you consider the same population in different at different times. So in generation 0, generation 1 is evolved with it, and generation. And you want to recover the dynamics, so basically how particles are moving towards time. So for that, you can use once again the optimal transport plan. Like you can move from generation to generation 0, sorry, to generation 1, and then generation 1 to generation 2 with the same. So you can recover a kind of trajectory of your distribution.
But to say you couple the ancestor and also the descendants.
Yes, exactly.
Okay, that's
exactly. And I particularly like this application because it is a versatile application in the sense that you can think of many many different populations. So, for example, optimal transport have already been applied on gene, like expression of gene. The population are gene, and each time so the expression of gene are different. You can also, for example, you can also think about like how sapiens moved in the earth toward time, or at the right it's like languages. For example, you can say, oh, okay, from Greek there is Latin, and from Latin there is Spanish, and you can move that kind of. You can find that kind of dynamic, and it is branching friendly in the sense that if you have one cluster at the beginning, it can be divided or into other cluster, or from two clusters one cluster. It is branching friendly.
It's like people lost also about there, because in a way you always needed the same amount of mass from one to the other, but how do you guess the mass your descendants? Not everyone has the same amount.
Yeah. So indeed, it is a big assumption to consider that the two distributions have the same mass, and I'm happy you're asking this because yes, it's kind of my work actually to deal with the distribution that doesn't have the same amount of mass. So basically, what we are doing is to consider the unbalanced optimal transport. So instead of having like a strict restriction of masses, you will have a smooth restriction of masses, and so you can deal with distribution with the different amounts of mass. Okay. So just to make a little break on the Wasserstein distance, so we saw that the Wasserstein comes with a unique transport point, which is sparse. It captures a detail of the distribution in the sense that you have a geometric idea of the geometric information of the encode in the Wasserstein distance. It's a suitable loss for machine learning, but the computation cost is quite heavy, like n cube log n with n the number of atoms. And we saw that there is many applications inside.
Especially for machine learning, you have some sort of distance between trees suitable also?
For trees,
For trees, yes, because some of the last problems of branching there were you must have some sort of distance between trees.
so yeah, so trees is more complicated because with the Wasserstein distance, you must have like a distance in the same domain, like the two distribution must be in the same domain. But this application doesn't deal with trees. You can just think about like this kind of thing, like in the plane, and there is a particle. No, not comments. So yes. So now I will talk about some statistics of the Wasserstein distance. Sorry. Because as we saw at the very first slide, we only have access to empirical distribution and not from the true continuous distribution. So the question is quite natural, is to ask, is this empirical Wasserstein distance is close to the true continuous Wasserstein distance? And the response is no in general. So it is a bad scenario. It is a pessimistic result. So you have this kind of estimator. So let me just make this clear. So this time, that you have an upper bound and a lower bound with a constant, and then so that's the upper bound and the lower bound. The same thing, but with another constant. So it basically means that you are converging very, very slowly when the dimension is high, and the higher the dimension, the slower you are going to converge. So for example, I took the example of a dimension d is equal to 255 times 255, which is basically an image.
P2 LB is the probability.
Sorry?
P2 LB is the.
I'm not sure to understand
The extension. This is the probability, no?
The pro.
New.
Yes, new and new are probabilities. Yes.
Yes, that is in our way.
Yes, exactly. And so in this example, with that dimension, when you want a precision which is smaller than 0.1, you will need a number of atoms which is very, very big. So the thing to understand is that when you are computing the Wasserstein distance between, for example, the concept of face who are smiling and face who are sad, with empirical distribution, it is not representative at all of the true Wasserstein distance. So the thing to understand is that you are overfitting, meaning that you compute something that is close to the data you have and not what your data are representing. Okay. So this kind of sample complexity can be computed in practice. So in this example, I took the continuous distribution to be Gaussian distribution, like usual Gaussian distribution. So the Wasserstein, in particular, the Wasserstein distance is 0 because they are two times the same one, and the empirical one are different because they are different something. And what I did is that I compute the Wasserstein distance in this slide, and I increase the number of points. So and it's a log domain. So basically, you have like the slope represents the power, this power over there. So you can see that in low dimension, it's a slope which is a decrease in quite nice, but in high dimension is almost constant for. So yes, it's not converging toward. Okay. Yep. Yes. Yes. So this kind of problem of overfitting is quite known in the statistical community. Sorry, and the general idea, sorry, in statistic in parametric statistics is to penalize the variable we are minimizing. Sorry. So penalization means that you want a variable to be more simple. So it is the basic idea. So for example, in statistics, if you are taking like optimization, which is a square Euclidean, you will have a problem of lasso when you are considering the square problem. So that's exactly what we are going to do. Okay. Is that we are going to penalize over the transport plan. So we minimize on the transport plan, so we can penalize on the transport plan. And it is the first proxy, so the first Wasserstein-like resistance that we are introducing, which is called Sinkhorn. It was introduced by Marco Cultori in 2013. And we penalize this transport plan, but by negative entropy function. I will try to make this a bit more understandable in the next slide. So as all of organization formulation, it is a compromise between fineness and complexity, meaning that if you have lambda equals 0, you recover the a certain distance, and the complexity of the model is quite heavy. But with a great fineness, but when a lambda is very large, you have a complexity which is lower and a lower fineness. The nice things about this entropy, this negative entropy penalization is that the objective function is now strictly convex, not only convex. It is faster to compute. At only it is square in the atom, and the sample complexity does not depend on the dimension anymore. So that's the big thing. Like high dimension, there is no problem. So I like to think about these two last points as being the same idea. Like if you have a model which is quite simple, it will be more faster to compute and have a better complexity. So yeah, it's kind of the same thing. So Sinkhorn, instead of computing a one-to-one correspondence between atoms, it will like blur the transport plans, meaning that you will have not a one-to-one, but a kind of mix. So the matrix will be more like this, for example. So that's the entropy. The greater the entropy, the more like blur you will have, and the lower the entropy, the more one-to-one you will have. Okay. So the thing that it's worth mentioning that when lambda is equal to 0, you recover the Wasserstein distance, and when lambda is plus infinity, up to a renormalization of a bias, you recover like the maximum mean discrepancy distance. So meaning that this is like Sinkhorn can be seen as a MMG, which is more fine, more that's it. So it is not automatic. Like when D large, you will have to have more penalization, which is quite intuitive. But the thing that is not intuitive is that the trade-off between model complexity and error is not continuous. So on the left, there is I got like the kind of graphic usual graphic with the least square problem, and on the right it was Sinkhorn, meaning that if you want to have if you have a lambda which is a bit more lower that what you need, you will recover a very bad rate of convergence. So there is a kind of threshold in this number. Oh, sorry. Okay. So we can do the same thing as we did before with the Wasserstein distance, with increasing lambda. So we saw that when lambda is small, there is a kind of same slot for the convergence, and when you increase the lambdas, even in high dimension, you will converge fastly. And in this case, for example, when the dimension is 47, you have a threshold of lambda which is around 8.5. Okay. I'd like to mention also that Sinkhorn is not the only penetration you can do on the transport plan. You can ask for your transport plan to be a low rank, so matrix low rank. So you will fix the rank, in this case R, and ask the transport plan to be low rank, so basically by block, this kind of thing. And you can think of low rank methods as group Sinkhorn, like we are doing a group lasso and stuff like this. Okay. Just to mention also that it is not only about the sample complexity, it is a more general problem, like things are way better and way nicer in the Sinkhorn case. For example, you have a CLT in the Wasserstein case, but which is biased, like this is not the good term, and unbiased on the Sinkhorn case. And the same with transport plan. We do not have like a speed of convergence of a transport plan in the Wasserstein case, but we have a CLT and the speed of convergence in the Sinkhorn case. Okay. So just to make things clear about Sinkhorn.
Excuse me, this is a theorem?
Which one?
The previous one?
Yes, this is a theorem.
So a theorem which is the dependence of P in pi?
So no assumption on pi. Just like you have empirical pi and continuous pi. So yeah, the assumption is that probability must be continuous. But
yeah. And what is the role of lambda? Because we saw that there was some kind of discontinuity on lambda.
Yes, so yeah, but basically what all this result is that when you have a lambda large enough, yes, because as we saw, like, for example, is lambda too small, you don't have that kind of rate. So yeah, for lambda large enough, you will have this. Yeah. Okay. So
lambda depends on the dimension?
Yes, it depends on the dimension.
Oh.
Sorry?
Oh.
It is not clear because it depends on the distributions, but yeah, it depends on the dimension. I think depends on the diameter of the distributions. Yes. So you can think about Sinkhorn and low-rank methods. We saw that they penalize the complexity of the transport plans. When lambda is large enough, you have a sample complexity which is optimal, which the computation cost which is smaller than the Wasserstein case, and it is a kind of a compromise. So in practice, all people that already deal with Sinkhorn, so that tuning this hyperparameter lambda is not easy in practice. And I lied a bit when I told you about the application of the Wasserstein distance, because like most of the applications are dealing with are using Sinkhorn instead of the Wasserstein for statistical and computational reason. Okay. So now it's time for me to introduce my contribution on this domain. So the idea is kind of simple. Instead of analyzing on pi, we will consider a subset of the huge subset U, which we call V. So we will show how to construct V and what kind of result we can have. So just to have a quick recap. So U is called the Birkhoff-Politov. So we saw that it is a space, a subset of positive matrices for which row and columns sum to 1. It is convex, and the vertex has a permutation of matrices. So in particular, there is n factorial vertex, which is quite big when n is large. And a nice thing to think about is you can think about Sinkhorn being smoothing this Birkhoff-Politov. Okay. So the first definition we can say is that you can construct V. I simply consider all the direction on the sphere S. You will project your distribution on this direction, and then you can compute the transport plane associated with each direction. So you consider V being all the transport plane obtained on the direction. So on this example, we will take, for example, first direction on this one, project your distribution. So this orange will go there, and this will go there, and this one. Compute the transport plane. So it is a one case, so it's only sorting. So this transport plane will make a correspondence between this one and this one, and then infer this transport plane, this one-dimensional transport plane will be used on the original distribution. So you will map this one on this one and this one on this one. So this is a first transport plane, and you have a second when you are considering this direction. And in this example, there are only two transport planes, so you can take maybe for example this direction and this direction, and you will cover one of the two transport planes. Okay. You can also define it's the same definition V by considering a pivot measure. So in purple in this example, and computing the Wasserstein distance between your phase distribution in blue to the pivot measure, and to the orange to the pivot measure, and then how can I say? Use these two transport planes to construct a new one. So basically, what you are saying is that okay, there is a correspondence between these 2 points, so I will make a correspondence between this blue and this orange. So when you are computing the distances, you are not computing like this one plus this one. You are really computing this one, but you will make the transport plane with the two other ones. And so V is the set of all the transport planes when the pivot measure is supported on a line. And for people who are familiar with optimal transport, so as strong links with what we call a linear optimal transport. So it is a theory when we want to linearize the Wasserstein space with a net to space. So just to mention some of property of this subset V. So it is a set of permutation matrices because it is a set of permutation matrices because it is transport point of projection of distribution. So all the elements of V in particular are vertex of U. We saw that the vertex of U are permutation matrices. And the things is that V is much smaller than U. So I put a table computing the number for the cardinal of V and vertex of U. Okay. So the first thing to say is that the cardinal of V depends on the dimension, which is not the case for U. And when the dimension is greater that's the number of atoms, you will recover the same number. So yes. And yes, I think it's time to mention that all my presentation was dealing with empirical measure with the same number of atoms and a uniform mass. But actually, you can do everything with like empirical distribution with masses with the different masses and so on. Okay. And now we introduce slice Wasserstein geodesic. So slice Wasserstein because we use the concept of slicing, so projecting on the line. And generalized geodesic is the idea that we use a pivot measure. So it is the same estimator as Wasserstein. Instead of minimizing over the set view, we're minimizing over set view. So yes, and what we prove is that mean SWDG is a suitable loss for machine learning. So it is a proper distance, metrize the weak convergence measure. And there is a translation invariance property which is full in some application, and there is a sparse transformation. And in terms of optimization, it's much more simpler because instead of minimizing over P and theta in B, you can just minimizing over all the direction on the sphere. And so you can perform like a random search in no dimension and validation when you are in high dimension. Okay. In terms of sample complexity, we have an optimal rate of convergence for mean SWGG. And in fact, we proved a more general result. So instead of projecting on the line, you can think of projecting your distribution on a subspace of dimension R. So for example, when you are in R3, you can project on the plane. Compute the Wasserstein distance on the plane, and leverage the two-dimensional transfer plan in the higher dimension. So you will have a rate which depends on the subset you are projecting on. And the proof is based on some curvature inability of the Wasserstein space. Okay.
And maybe got lost over there. So what happens if R is equal to 1, you get n minus 1?
Yes, okay, so yeah, it's when R is less than 2, you have minus 1 over 2. You can do that. And yes, I'm thinking about one thing is that there is a nice application also when you are considering like a pivot measure which is a discrete. So basically the dimension will be kind of 0 because it is discrete, and you also have this minus 1 over 2 Okay, so just to make stuff clear on the SWGG, so it is a suitable loss for machine learning. Instead of penalizing the transfer plan, it penalizes the size of the Markov polytope. It has an optimal sample complexity and much more faster than the Wasserstein distance. Like it is only sublinear in the number of atoms. And also the thing which is nice is that it gives a transfer plan which is sparse. In contrary to Sinkhorn, as we showed, there is a kind of blur transfer plan because of this entropy penalization.
Yes, but I suppose that we have sense if can you put the previous one?
This one?
The previous one. Yes. If the minimum SWGG between mu and B is representative in some sense, is a good parameter, something between mu and mu. That is to say, if the symmetries are well represented in mu and mu.
Yes, so you're asking is
because you are comparing expected value between that and the other one.
Yes, it's clearly that that's a good point. So I'm not sure to understand, but I think you are mentioning that this one can be not representative, but yeah, yes, exactly. So yes, so I will try to convince you in the next few slides that it's representative. But yes, it's a good thing to mention that this one is not converging to the true Wasserstein distance, it's converging to a proxy of the Wasserstein distance. So just to compare Sinkhorn and mean SWGGs, we penalize on the transfer point as I said, the algo is more faster and the statistics are optimal without parameterization of the lambda and there is an complete transfer point of Sinkhorn and a sparse transfer point for so yeah, to try to convince you, I will talk about two applications of mean SWGG. So the first one is a kind is to prove like a kind of weak convergence of measure in the Wasserstein space. So basically, what we are doing is that we start with two distributions. So one target distribution in blue and one random distribution in red. And you want to map the red distribution towards the blue distribution by simply minimizing the distance. So we compare to slice and max slice, which are the typical distances used in this case, like for example a GAN scenario and stuff like that. Yes, and I should yes, okay. Oh yes, I'm sorry. Like the small animation are on my computer, so I can show you. But in practice, what it's doing is that SWGB is converging quite well when the distribution is complicated. For example, in this cluster case, and slice and max slice are can struggle to converge to this cluster. And okay, so the second application, so essentially no animations. I'm sorry. So it is a shape matching problem. So basically, we have two shapes. You can add a bit of noise on one of these shapes, and you want to make matches of two shapes. So what we are doing is that we are doing a one-to-one correspondence between these two shapes, and then you solve a focused problem, and you iterate until convergence. So another one-to-one correspondence, another focus problem. So this kind of problem are usually dealing with the nearest neighborhood correspondence. So basically, you map only to the closest point. And so what we are observing is that it's much more better to compute the mean SWGG problem compared to the nearest neighborhood, and much more faster than computing the optimal transfer. So typically, in this kind of example, you can deal with the point clouds with like 100 of points. So Wasserstein distance can be computed in this scenario. And also, I would like to mention that you can compute Sinkhorn in that kind of scenario because of this one-to-one correspondence assumption. So Sinkhorn, there is like a bit of noise in the transfer point, so you don't have one-to-one correspondence. And once again, yes, worth mentioning that mean SWGG, okay, so the shape are matching and nearest neighborhood you can struggle much more. Okay, so thank you for your attention. Also, as Philippe said, so this work on SWGG has been accepted at MORIFS 2023. And the statistical properties that I mentioned are still in progress, so it is not on the paper. Yes. I don't know if there is any question. I will be happy to answer them.
Yes. Yeah. Thanks, Guillaume, as much as you want. Thank you, I don't know if there's any questions. You can ask in English, in Spanish, in French, in Arabic, Latin, Esperanto. I will ask a question to break the ice. Can you go back to slide 38, I guess?
38.
This one. Maybe 37. The definition of the SW, the definition of B.
Yes.
So maybe before this.
Yes, I was
No?
sorry.
This one? And the next one? Or maybe what was the definition of so when you take the
So there is two definitions. This one is with a projection and permutation.
okay.
And this one is with optical measure.
The next one?
And the next one is some property only.
And the next.
Oh, no, sorry. And this one. Yes, no, sorry.
That one.
Yeah, okay.
Yeah, maybe there's something I don't understand because you're in equation 14, you're taking the minimum over B, this set you defined. Okay, so I have two questions. First one is that in practice, how do you search over B? Do you sample from the sphere?
So yes, so I was a bit quick on this. So basically, is that okay? The minimization of the transport plan over V can be replaced with the minimization over all the direction. So actually, you are looking for a direction, not for a transport plan. And so what you are doing, for example, let's say in a random search, you are taking a direction, compute the SWDG for this particular direction, and then take another one and compare if the cost is lower or better or similar.
But something that maybe it's because I don't understand it, but in some pathological cases, but cases that are not too rare in high dimension, you might project into a direction that is orthogonal to the support of both distributions. So all the support gets collapsed onto one point, and then the distance is zero.
Yes.
You're taking the minimum, so you might find that projection.
Yes. So actually, yes. So indeed, that was one of the motivation of using this kind of method instead of slice, because actually, when all the points in the generic case, of the point are projected on the same point, the transport plan will be fully blurred because, or maybe a random one-to-one coordinates. That no matter. And then you are using not the point that you project on, but the original points. So and so the matrix will be not optimal at all. Like
Any more questions?
yes.
Could you ¿cómo decir? Poner la slide
The slide 29.
Yes. Yes.
Okay. Why using a large penalization lambda converges to the maximum mean discrepancy?
Yes. So that's a good question. So okay. So there is a kind of thing that was under the carpet. So that is not exactly the Sinkhorn divergence. It's like unbiased Sinkhorn divergence. That's the first thing to mention. And then it's MMD, but with a particular kernel, with minus the cost matrix. So maybe I can write it down. So okay. So you will define SD. It's equal to S mu minus H. So this is the unbiased Sinkhorn. And when you have full entropy, the transport plan will be fully blurred, like every value are the same. So you can see what I can see on transport plan. And so basically, the PIG on the matrix will be 1 over n squared for all the E, for all E and G. Okay, and so just putting this one, so this one will be some check. And you sum over G, and so we can replace this one, we can find this one, check. And then putting these things also here. Okay. Like, so you will have this kind of things. The parts of it, okay. And this one is exactly like the MMD when you are considering your canal to be minus 1 more event. Is there any other question?
Okay.
I have, but unfortunately, we have to move to outgiven by some somebody related to CRM, so I will come to see you at some.
Anyway, Guillaume is staying until January, so in case you want to discuss any of these further with him, he will be that's January based on the 6th floor in the East Tower. So you can drop him an email and talk about this. Thanks everyone for listening. Thanks, Guillaume.